Hello, everyone. Thank you all for joining us today. I'm Bob Crossan, Managing Editor for Water and Waste Digest. On behalf of Water and Waste Digest and our sponsor, Kaeser Compressors, I'd like to welcome you to today's presentation titled, How to Evaluate Blowers by Application. Blowers are a critical resource for wastewater treatment plants or water reclamation facilities, so choosing the best blower is vital for plant operational success. No plant is stagnant, so a one-size-fits-all approach often provides less than ideal operational scenarios that plant operators must constantly adjust to. Taking the time during the blower selection and evaluation stage can go a long way to improving performance and control of the process. In this webinar, we will explore how to evaluate blowers in wastewater applications to ensure the best blower is chosen, as well as control options for these applications. Scenarios include constant depth and variable flows, variable depth and constant flows, and variable depth and variable flows. We'll get started here in just a few minutes, but first a little housekeeping. You will notice on your viewer that you have the ability to ask questions. We encourage you to ask questions, and we'll try to answer as many as we can at the end of the presentation based on time availability. Any questions we do not get to, we will answer offline. Participants in today's webinar also earn 1 professional development hour. I'll give you directions for receiving your certificate at the end of the webinar. Our presenter today is Stephen Horne. He is the Product Manager for Blower and Vacuum Products at Kaeser Compressors, Incorporated. Stephen has over 15 years of experience with the design and function of blower systems and wastewater aeration applications. In addition to being the primary instructor for blower products and applications in Kaeser's factory certified training program, Stephen is a frequent public speaker and writer on topics related to improving performance and efficiency of blowers in wastewater systems. Stephen plays an active role in the Compressed Air and Gas Institute's project to develop performance testing and reporting standards for blowers and low-pressure compressors. Currently, he serves as chairman of the Blower and Vacuum section that heads that effort. Stephen also holds a bachelor's degree in mechanical engineering from Virginia Polytechnical Institute and State University. Now, I'll turn it over to Stephen. Take it away, Stephen.
Okay, thank you, Bob. Welcome to everyone, and thank you for attending. For the webinar, we'll take a look at the methodology to evaluate various wastewater applications for blowers. As you know, there are many new technologies in the blower market, and the tendency is to favor the newest and most advanced technologies. But are they always the best suited for the application? Well, today we hope to be able to provide you with a methodology that will help you in making this determination. There are many processes and applications for blowers in the wastewater industry. We have selected a few of the more common applications for review today. These include processes which have steady fluid depths and variable air flows. So these are most commonly your aeration systems. Processes with variable fluid depths and constant volume flow, such as a digester. And finally, an application with variable fluid depths and variable volume flows. The system for these evaluations has similar foundations. This foundation includes creating a model of the process, acquiring data for the blower, populating the model, and then finally making the evaluation. For a fair evaluation between equipment, it is critical to base the evaluation on a model of the process or the system. These models can be created by various means. With data acquisition equipment, powerful computers, and advanced algorithms, the possibilities are endless. So for this session, we'll aim to simplify these evaluations. Still, with this methodology, you're able to scale up or scale down your evaluations to satisfy your project needs or your technical limitations. If you're like me, the more advanced the process, the better, but this does not mean that a simplified approach cannot be effective. By being strategic in the creation of your model, you can create an accurate evaluation model which can be valuable for the future of your evaluations. For many wastewater plants, the demands are not fixed. They vary daily, seasonally, and year by year. If we were to take a log of the flows, pressures, and hours of these plants and plot them year over the year, they begin to take on a bell curve profile. Once you have this profile curve, you then can divide this curve into segmented pieces, giving you a unique data points for evaluation. Depending upon your needs, you can make as few or as many segments as you desire. Certainly, the more you create, the more accurate your model becomes. However, at a certain point, adding more data points does not add to accuracy, although it does add to the complexity of your evaluation. So for today, we'll take a look at 5 segments, as this is something that we can easily do by hand. Now, foundations of this point will be a Gaussian-like distribution curve like you see on the screen now. Note that you have distribute this curve however works best for your process. This represented by the blue, gold, red, and green curves. So depending upon how your process is, one of these curve colors may more accurately represent your process. So you almost have to pick and fit as needed. I took this graph from Wikipedia, so you can find it here, as well as a deeper discussion on Gaussian distributions, if your mathematic mind so desires. All right, let's start with scenario 1. Scenario 1, I think, is a very typical application for blowers in the wastewater process. To me, this is your run-of-the-mill basin aeration. The tank depth is constant, and the airflow is being varied to chase a control variable in the basin. In most cases, this is dissolved oxygen, or DO. Of course, there are other control variables being used out there today to control blower speed, but for today, we'll pretend that it's dissolved oxygen. For this scenario, the basin is 24 feet deep. This works out to about 10.4 psi-G, and the flow range we'll say is 330 to 1100 CFM. We'll include a VFD on the blower, which we use to receive the dissolved oxygen signal and regulate the blower speed to match the basin requirements. So the first step in our evaluation is to create a model of our system. We know that the range is 330 to 1100 CFM, but we don't know much more. So what point should we use for our comparison of the blowers? Well, I think the most common solution is to pick the maximum flow, but this presents 2 problems. One, as we can see in the graph, the blower rarely runs at the maximum speed and flow in this scenario. And 2, a blower supplier can pick a machine that is excellent at the design point, but not as stellar at the other points of the control range. This results in the end user never realizing the full predicted benefits of the system. For a more realistic evaluation, we can apply a distribution curve for our flows and assign the expected hours of operating for these points. If there is no history for the process, we can take our Gaussian logic and create a profile and apply values. Note that we do not need to be too religious about the application, and if you know the relevant design points, use those points. It's always best to use data which you have collected from the site rather than making up data. But if you have no data, better to make some sort of model than to have nothing at all. Here, our selection indicated flows and assigned the noted hours. We find that the majority of time for this model is spent at partial load and not at the maximum or minimum values. So our machine should provide good performance at this point to maximize our investment. So with the model created, it is now time to take a look at the blowers. For VFD units, it is always good practice to request 5 data points. This will be min speed, maximum speed, and then 3 evenly spaced speeds in between. This provides a nice performance curve that can be interpolated to find the desired data points that you created in your model. Another important factor is the presentation of the numbers. In this graph, the blower shaft power, input power, and specific performance. From which this graph can be created. Historically, blower shaft power has been the metric for machine comparisons. However, the shaft power does not tell the full story. A blower system has a series of components that are required for typical operation. This includes silencers, drive components, filters, and possibly valves. Depending upon the technology, there can be pumps for circulating oil or water in the system, and also most machines nowadays include a cooling fan. All of these should be factored into the input power number. These are all critically important values, but the VFD in example is critical. VFDs have greatly increased the versatility of machines and opened new doors for process control. We can all realize that from historical significance. We can also see how varying machines' output to match the process can reduce power costs in comparison to a fixed speed unit. But how does one VFD unit compare to the next? Well, there are several efforts to create standards to assist in this effort. The graphic above is based upon ISO 1217 Annex E. This is a VFD code for driven air compressor packages, which nicely compiles data for the data points provided above. While the numbers above are from a fictitious machine, we can see how this format is helpful. From the chart, we can see how the relative performance of the machine drops off at the lower end of the performance curve. So this is what you see here, where we're at 0.5 at max flow. We're at 4.04 kilowatt per 100 CFM, but that now drops off to 4.63 at the low end. This is a result of losses in the air end, as well as the electric drive motor and the VFD. The ISO standard is also based in measured values and not so much estimated values. The losses in the motor and the VFD are not linear, so by saying that the blower shaft power is plus 8% from this input power does not always apply across the entire range of the unit. Some technology, this impact is not as great as others. For this efficient blower, we can see the curve is relatively flat. So for our next blower, which we call the affordable blower, we can immediately see the difference in performance, particularly by the shape of the curve. In general, the performance is not as good as the efficient blower, and the tail off of performance is more pronounced at the lower end. So this machine here, you can see we start at 5.31, and if I'll read you what the other one was before. It was 4.04, and we drop off dramatically at the bottom end to 7.2, whereas before we were 4.63. As notable by the name, the blower is more affordable. However, as we stated, the performance is not as good as the efficient blower. So how does this translate to our plant model? Well, let's see. In this slide, we now can see the two blowers as well as our plant model all at once. The first thing we notice is the flows from the plant model does not exactly match the flows from the machine. This is to be expected, as we have requested blower data for min flow, max flow, and then evenly spaced points in between. Not to fear, we can simply interpolate the blower data for desired flow values of our model. And if you're not familiar with interpolation, you're a simple Google search away from interpolating data points, and you'll come up with a calculator which you can utilize for making these calculations. By having multiple data points, our interpolation will become more accurate. The target will be input kilowatt. With input kilowatt, we can calculate the yearly kilowatt hours for this given data point. This effort is replicated for each of the model's data points we are investigating. So now, having solved for kilowatt hours for each of the 5 data points and for both machines, we can do a summation of the kilowatt hours. This total will be seen under this total can be seen under efficient blower, which is 285 kilowatt hours, 285,000 kilowatt hours, and for the affordable blower, which is 341,000 kilowatt hours. So the efficient blower tips the scale at 24% fewer kilowatt hours, which is a significant number. This, as well as sounds more efficient, but where does that mean for dollars? To figure out how much money this results in, we must take the kilowatt hours between the efficient blower and the affordable blower and then multiply them by what the plant pays for power. In this example, we're going to assume 7 cents per kilowatt hour, which will be constant all the time, which gives us $18,000 a year for the efficient blower and some $24,000 a year for the affordable blower. This is a difference of about $5,000 per year. So over 20 years, this works out to $116,300. So the real question in all of this would be the difference in purchase price and the potential installation cost. If the difference is $20,000, the efficient blower makes a lot of sense. If it is $100,000, then it does not. So it really comes down to your electrical costs and your investment costs. So this concludes the section on constant depth and variable flow. For efficient blowers, which cost more, this is often the area of a plant or application where these newer efficient blowers make the most sense. For more on this, let's take a look at some other applications. Okay, so hung up here in the slides a little bit. Okay, so scenario 2 involves a treatment basin that uses constant airflow with variable fluid depths. Here we find a blower running at constant speed with near constant airflow, and the depth of the tank is variable. As the tank depth rises and drops, the back pressure on the blower will change. This will change the power consumption of the machine and affect performance gains and energy savings. Let's see how much this impacts these figures. Excellent. Again, for this evaluation, we will look at the requirement of a 950 CFM blower at pressures 4, 6, 8, and 10.4 psig. You can see roughly what this equates to in tank depth over there on the right. So we're looking at 24, 18.5, 14, and 9.25 feet. These pressures will be determined by the rise and fall of the depth again. The selected pressures for the evaluation are a bit random, but we need to start someplace. So an even split is a good starting point. Again, if you have prior knowledge of the process, where you know you're going to run at a specific fluid depth for a given time, use this knowledge. A rough estimate for pressure is that 1 foot of water depth is about 0.4335 psi. So at your 10 foot, that's 4.3 psi. This is the amount of pressure it takes to make bubbles in a basin. Actual blower pressure will be higher to accommodate for flow losses through the pipe, valves, and the diffusers. As with the previous example, we start with creating a model for comparison purposes. In a similar fashion, we apply an hour distribution, however, this time against the selected pressures. Here we assume the majority of time will be spent at the midpoint of the distribution, so it has the most hours allocated. Depending on the process, this could be a fair representation, but again, depending upon the process. It can make more sense to favor a higher or lower pressure. The more accurate your distribution of hour represents the actual case, the more accurate or more representative your results will be. Here's our first blower, the efficient blower again. One thing to note is that while the machine is considered to be an efficient technology, which it is, its efficiency does vary or drop off as our pressure decreases. In fact, the power values plateau at a certain point. This is good demonstration how the importance to acquire multiple data points from the blower supplier. A single data point may be misleading as the technology may have unforeseen or unexpected limitations, and it is better to identify these limitations during evaluation rather than at the installation. And here is our affordable blower technology description. If we compare this to the efficient blower, we can see how the data points where the efficient blower is certainly more efficient and the points where the affordable blower is now better. Hopefully, we are now seeing the importance of our model and the hour distributions. Additionally, we should now be able to see how much the application can impact power consumption and usage of the technologies. For here, no interpolation is required. This is a fixed speed blower, so all we need now is the power consumption at each pressure, and this is what you would request it from the blower manufacturer. It's as simple as entering your power values in for the required pressures. We can do this for each of the blowers, and we are ready for the next step. Now, multiply the hours of the kilowatts for each pressure and again for both machines. This produces kilowatt hours for each of design pressures. Finally, a summation of each of the 5 points by the blower provides a total kilowatt hour for each unit technology. Once more, multiply this kilowatt hour by the electrical cost, and you have an estimate for the annual power cost. In this example, we again find the efficient blower is indeed better on annual cost over the affordable blower, but is not as dramatic as before. The prior example showed 25% improvement, but with the variable fluid depths, this has been cut more than half to 9%. This 9% is still a substantial improvement, but now you must examine how long the payback for the difference in investment and weigh this with the client as to the best direction for the project. Okay, so at this point, we have looked at constant fluid depths and variable flows, variable fluid depths with constant flows. Now, we will up the difficulty a little bit and look at variable fluid depths and variable flows. This is very similar to the prior example, but now we'll throw on a VFD on the unit, and the client wants to take advantage of this as the flows will vary with the fluid depths. Okay, for this scenario, we use the same setup as the prior example, with pressures of 4, 6, 8, and 10.4 psi. Again, you can see the fluid depths on the right. The factor for pressure and water depth is again remain at 0.4335 psi per foot, but now we have the VFD driven blower. Okay, so we can get the next slide. So as we get to the next slide, this will be a bit repetitive at this point, but again, we need a model for the system to make our evaluation with. This model is a bit more difficult to create and may require some assumptions or a best guess if there are no prior data to draw from. In this case, we selected a reasonable minimum flow and evenly space out the middle flows, then assign them to the previous supplied pressures. So these may or may not be a fair representation of the system, but starting with nothing, some reasonable assumptions must be made. As with the other examples, if the system data is available, it's better to utilize these metrics when creating your model, as a result in a more accurate evaluation. Okay. Next slide. All right, the next step is the blower data. In contrast to the prior examples, this data is a bit more difficult to compile. To acquire the data, you can specifically ask for these data points as done here. You want to get your 5-point curves for each pressure. If you get the 5 points, you get a 5-point curve for each pressure, then you have to do all the interpolation. So in this scenario, we just requested flows at a given pressure and got them from the manufacturer. Otherwise, you have to do interpolation. So here, we source the data for desired points, which simplifies the effort on this example. So we're still looking at the efficient blower. Next slide will be the affordable blower. Okay, here we go. So here we find the data for the affordable blower. Again, this is not as good a performer at deep levels, but this technology gains at the low pressure side of the system. Okay, next slide. One last time, we populate a chart with the kilowatt values. In this view, we can again see how the affordable blower technology gains on the high efficient machine as the pressure falls. Still, the running hours are limited with the model at these lower pressures. Next slide. Okay, here we find the results of our modeling. The first point to consider in the reduction in power costs is the comparison to the previous example. Adding the VFDs and varying flow in the fluid with varying fluid depths reduced the power by 20%, 319,000 versus 250,000 for the affordable blower. Next, we find that the efficient blower is again a better performer. The $2,000 a year would need to be weighed against the cost of the machines to determine if the return on investment was worthwhile. But clearly, varying flows with the fluid depth did save us a significant amount of money and showed the value of the variable frequency drive. Next slide, please. Okay, so hopefully these three exercises demonstrated a valuable methodology for evaluating blowers. While working through these scenarios, we learn how the application or the process can impact your decision making. Additionally, modeling your process can provide insight into how the prospective blowers will operate within your system. Most systems are dynamic, so static evaluations do not accurately represent how the units will accurately be utilized. Generating a model that accurately or partially represents your system or process can allow a more realistic machine evaluation, which will lead to a better blower selection. As we saw, the efficient blower technologies now in the market always outperform the affordable option. However, the impact on your power costs, pressures, and operatings will impact the return on investment and likely your decision making. Okay, next slide. So we've talked about the applications of the blowers and how they work together, but let's get into a little bit more about blowers themselves, and maybe this might also provide some additional insight as to why we are seeing those numbers vary like we did. So within the blower market, the first one we're going to talk about are dynamic machines. And dynamic machines work by accelerating the inlet air in an axial direction, axial or radial direction. For blowers, this is typically radial. Examples are multi-stage centrifugals, turbo compressors, and most recently, high-speed turbos. Let's see if we can get I have a nice little graphic to show you guys and see if this works. Maybe we could hit the next slide for us. Maybe it'll animate. Here we go. Hopefully that moved for everybody. But for these dynamic machines, the acceleration of air molecules generates what we call kinetic energy. The blower transforms these high velocities into another form of energy known as pressure. This happens through the acceleration of the air into a diffusers to allow a low flow speed, widening across the section of the pipe of the compressor and the impeller. The kinetic energy is thus reduced, resulting in an increased pressure as a result of conservation of energy. Okay, let's go to the next slide. And here we'll talk about displacement machines. On this other slide, next slide please. Here, well, we've already done the compressing, but as you can imagine, that plunger was pushing that blob of air against the wall. So on the other side, we have displacement machines. Here, the concept is a bit easier to grasp. A displacement compressor creates pressure by squeezing air or continuing to drive air into the pipe where air is already compressed. This is like cramming more trash into a full trash can. This is what we call positive displacement. Instead of flinging, we are squeezing. Okay, next slide. So we'll spend some more time looking at the displacements. So in the world of displacement machines, and the water market is most accustomed to lobe or roots blowers. This is the one on your left. And the screw blowers, which is the one on the right. So next slide, and we'll see the screw blower pop up. So looking at the one on the left, this is a lobe blower. A constant volume is moved through the air without volume reduction. Pressure builds up in the piping downstream from the compressor through the injection or buildup of air molecules. This is referred to as external compression. Again, think of this like forcing more trash into a full trash can. At the screw, the rotation of the screw results in a gradual reduction of volume. This is referred to as interior or internal compression. The air compressed in this way is ultimately forced into pipe. The volume ratio affects the level of internal compression. Next slide. All right, see if we can get through this animation a little bit. Just hit the next tab a couple times. The rectangular area in this diagram is spanned by the flow rate through the compressor and bridged by pressure as a difference. This represents the compression work. So if we go 1 to 2 to 4, there we have this rectangle which represents the work done by a PD blower. The pressure represents a force and the rotation of the rotors to displace the volume at that distance. So our work is the area in the square. Going back to our examples, the height of the box represents the system pressure. As such, the more pressure we see in a system, the larger the box. The less pressure we have in a system, the smaller the box. Again, think adaptive pressure. Next slide. Okay. For most internal compression machines, the system pressure is lower than the internal pressure of the blower. Excessive compression followed by re-expansion of the excessively compressed volume occurs in the discharge piping. So here we have, before when we had the rectangular box, now we have this curved box. And if we hit the next tab a little bit, we'll see the intake for the blower, and then we'll see the compression up to the internal compression. We go by system pressure, and we go overshoot with the low and high pressures. To minimize the excessive work or energy associated with the excess compression, screw blowers have evolved in recent years to minimize the overshoot of internal compression. While using the correct rotary screw version, the energy savings amount to 25 to 30% can be realized. So here we are seeing our graphic, and in a minute here we'll see the overlay of the Lobe blower. So here we can see the green part represents our savings by the curved line of the internal compression, and the red area represents our overcompression. So if our system pressure is less than the overcompression, we have to make sure that our savings justify it, which is why the new screw blowers have been optimized with their internal compression to minimize the overshoot. Okay, next slide. The performance of the air producer is only part of the story. The air must be drawn through and pushed out as several components. Each of the components in the package represents a flow loss, pressure loss, or a rejection of heat. To permit objective comparisons of different offers and related performance specifications, it is important to understand the different reference points of the flows and performance and the correct terminology. Otherwise, there's a risk of comparing apples and oranges. So if we can go ahead and hit the next slide so we get to number 10, we finish with that. So in ISO 1217, the compressor or blower block is described in Annex B. So this will be just an evaluation of the blower block and kind of refers back to what we originally discussed early on about how many blower evaluations were done just by the blower block and or blower shaft power. But again, any blower package includes both a blower block as well as silencers and these other electrical components. So to get an evaluation of the entire electrically powered machine, we have to advance to what we call Annex C, which will be the entire package. If we put on a VFD, then we utilize Annex E. And with Annex E, we get those 5 data points I referred to before regarding min flow, max flow, and then the points in between. But hopefully with this we can see how the acquisition of numbers from the blower supplier need to be accurate and representative to give a real evaluation. If we're just doing our evaluation based upon a blower shaft power, we are losing out on all these points 1 through 7, including our losses in the drive, our losses from fan and silencers, as well as consumption of power in the electrical cabinet. Additionally, hopefully we can see from the previous slides with the graphics for the work areas for the lobe blower and the screw blower, how those different applications we were looking at would impact the performance of the machine and also how much gains you're going to realize and then ultimately the return on the investment. Next slide. Okay. So for the 3 type of application scenarios, we have the application with constant fluid depths and variable flows, and then we looked at constant flow with variable fluid depths, and then finally we looked at both variable fluid depths and variable flows. We went over how to determine the specific performance of the blowers you are considering in context with the flow and pressure combinations you expect based upon your application. This will help identify the most efficient blower and quantify if the operating cost that you calculate will make irrational decisions and price as well as the operating cost data. Then we looked at types of blowers and related them to the operating characteristics to the applications. While some types may deliver better energy performance in one scenario over another, you have to look at the specific performance in the context of the expected operating range to compare and assess the energy consumption. There is no one type brand that is best for every scenario. So it's always important to, again, create your model, get your blower data, apply the blower data, make your evaluation. From your evaluation, you can evaluate your investment cost versus your return on investment and select the blower manufacturer and blower technology which best suits your project needs. Okay, well, thank you very much, everyone, for joining us, and I will hand it back to Bob.
Thanks so much, Stephen. Really appreciate the presentation. We do have some questions in here. Wanted to start with this one here. Does the ISO 1217 method tell me the total wire-to-air energy measurement?
Well, wire-to-air measurement is a unique term. ISO 1217 doesn't necessarily call it wire-to-air, but this is essentially what you're getting. So with an ISO 1217, you are measuring the output flow of the machine at the discharge of the unit, and you are measuring the input kilowatt. So this would, by measuring the output flow and measuring the total package input, you're getting the delivered flow and measuring all the power. So this would be your wire-to-air for certain, which includes a measured losses through the machine. But ISO 1217 refers us to a specific performance.
Gotcha, okay. We also have one here that's asking for some differences between types of blowers. It sounds like does a twisted lobe blower behave like a lobe or a screw blower?
Well, the twisted lobe is a bit of a mix to them. There are different types of twisted lobes out there. There are some where the inlet and discharge ports are arranged directly above one another. So the advantage here is the increased sealing strip, which reduces the slip through the blower, which does improve it, but it very much behaves like a lobe-type blower. And then where you offset the ports on this twisted lobe, what you're able to do is you're able to increase the blower speed, but there's still no internal compression. But the increase in speed does increase the performance, and that is very similar to what the screw blower does. But the screw blower has a defined internal compression, whereas the twisted lobes do not.
Excellent. And does this work for other technologies like turbo blowers?
Yeah, the analysis would absolutely work for both turbo blowers, lobe blowers, or screw blowers. The difference is going to be how the data is worked out in the evaluation. So getting the data from the manufacturer, you can still populate your model as we populate it with the lobe blowers, and I think that ultimately this would give you the most representative comparison across technologies.
Cool. We have another one here that's talking about air temperature, and again, if you have any questions, please send them in. We're going to be filtering through them here. Air temperature affects both air density and blower performance. What do you recommend as an evaluation for inlet conditions?
Well, your inlet conditions, ultimately you have to pick something. A lot of people will use what they call ASHRAE data, where they type in their location, and ASHRAE will give you the most representative temperature for your location. That will include both your elevation, your humidity, as well as temperatures. If you have drastically varying ambient temperatures, you can do that yourselves. Some people will look at something online, but I think that from the engineering community, the ASHRAE is the most accepted source for data for your installation.
Excellent. And it looks like the questions have died down a little bit, but wanted to let everyone know, yes, this presentation will be available after the webinar, and I'm getting to that here just now as we go into our wrap-up. That wraps up our questions and answers. Any questions we didn't get to, we will answer offline. Please stay logged in after you hear the webinar end to receive the PDH certificate for this webinar. You will be linked to a form with spaces for your name and email address. Please fill out the form with your name as you'd like it to appear on your certificate. The email entered should be the one with which you registered. The completed certificate will appear on your screen. You can then print it out for your records. So thank you on behalf of Water and Waste Digest and our sponsor, Kaeser Compressors, and thank you again, Stephen. We'd like to thank everyone for their participation in this webinar. This webinar will be archived at the same URL you used today and on WWDmag.com. Thank you so much for attending, and we'll see you next time.